This higher tier section is about electromagnetic effects. An electric current flowing in a wire produces a magnetic field around it. If that wire passes through another magnetic field, it causes the wire to move sideways. When the current flows, the wire moves one way, and if the current is reversed, the wire moves the other way. The interplay of these forces is the basis of the electric motor. Watch the next clip carefully to see how a motor works.
Inside, it's clear there's a coil of wire. Here's how it works. Built into the case of the motor is a magnet. Right in the middle is the coil of wire. It's free to rotate. And through these sliding contacts, it's connected to a battery. Current from the battery turns the coil into an electromagnet. The electromagnet's south pole is attracted towards the north pole of the magnet in the motor casing. So the coil turns round to bring them closer together. If nothing else happened, that would be the end of the story. The coil would just sit still, not going round. But just at the right moment, the sliding contacts flip the direction of the current. So the magnetic field in the coil flips too. Now the coil's south pole is next to the south pole of the motor. Similar poles repel each other, so the coil is pushed away and it keeps on turning. Half a turn later, the contacts flip the current again. So the cycle repeats. The coil never quite gets to where it wants to be, and it will keep on spinning until the battery runs out.
The interplay of the magnetic field in the wire loop and the magnetic field between the poles causes the wire to move. Reversing the current flow at the right moment causes the loop to rotate. A coil with more turns increases the magnetic effect. The force on the wire can also be made greater by using a bigger current or stronger magnets. In a DC motor, the current in the coil is reversed by using a split ring commutator. In an AC motor, the alternating current reverses the flow automatically. Now, we saw how a wire with a current flowing in it moves sideways in a magnetic field. Can the opposite be true? Will moving a wire sideways through a magnetic field create a current in the wire? Watch the next clip and see what happens.
If you'd like to hold the wire, well, I get the magnet, that's right. Now, if you move that wire past the magnet, now you should see a needle moving, can you?
Yes,
Yeah?
and that's current being generated in the wire.
That's right, yeah. Now, it also works if you move the magnet past the wire.
Right.
So it doesn't matter which is moving, one or the other, provided it's moving, you get electricity.
So the reverse is true. Moving a wire sideways through a magnetic field does create a current in the wire. This is called electromagnetic induction. Moving the magnet past a wire produces the same effect. It's the movement that creates the current. Reversing the movement reverses the current. Let's see what happens with a coil of wire. We know that a current flowing in a coil of wire creates a magnetic field in the coil. Will moving a magnet through the coil create a current in the wire? Watch the next clip and see what happens.
The children have connected this coil of wire to a meter. When a magnet moves in or out of the coil, a tiny current starts flowing. Electricity is induced. But it's a tiny current, and it stops as soon as the magnet stops moving. They found that a coil with more turns made more current. Moving the magnet faster helps too. The direction of the current depends on the direction of the movement. As the magnet goes inside the coil, the current flows one way. When the magnet comes out of the coil, the current flows the other way. The current flows in alternate directions, so it's called alternating current. It turns out that it doesn't matter if it's the magnet that moves or the coil.
So, a magnet moving through the coil does create a current in the wire. Moving the coil past the magnet produces the same effect. It's the movement that creates the current in the wire. Reversing the movement reverses the current. The current is made bigger by having more turns in the coil, by moving the magnet more quickly, or by using a stronger magnet. A generator uses the rotating movement of a coil through a magnetic field to produce a current. This is what the people used in the village in Sri Lanka.
Lionel is an electrician who's helped many villages to generate their own power. He fixed them up with a turbine, a kind of high-tech water wheel. When water from the tank hits these blades, it will turn the generator very fast. The generator works by spinning a coil inside a powerful magnet. The coil spins round because it's attached to the water turbine. The spinning coil cuts through the magnetic field. That's what induces a current. And so long as it keeps turning, electricity will keep coming out through sliding contacts on the end of the coil. Everything worked. The village lit up. Another corner of the world lights up for the very first time.
Although their generator looks similar to a motor, don't confuse the different ways the two devices work. An electric generator does the opposite of an electric motor. In a motor, a current flowing in a coil placed in a strong magnetic field produces a rotating movement. In a generator, rotating a coil in a strong magnetic field produces a current. One more useful electromagnetic device is a transformer. Transformers need alternating current to work. An alternating input current flowing in the primary coil creates a changing magnetic field in the soft iron core. This induces a magnetic field in the core of the secondary coil. This changing magnetic field induces an alternating output current. Remember, the primary and secondary coils are not connected electrically. The link between them is the magnetic field that goes through the iron core of both coils. The main use of a transformer is to change the voltage of an AC supply. If there are more turns in the secondary coil than there are in the primary coil, the voltage coming out of the transformer is more than that going in, a step-up transformer. If there are fewer turns in the secondary coil, the voltage coming out of the transformer is less than that going in, a step-down transformer. There's an equation linking voltages across the input and the output of a transformer. The primary voltage, Vp, divided by the secondary voltage, Vs, equals the number of turns on the primary coil, Np, divided by the number of turns on the secondary coil, Ns. The bulb in a table lamp operates at 20 volts. The lamp uses a transformer so it can be plugged into the 240 volt mains supply. The transformer has 300 turns of wire on its primary coil. Calculate the number of turns in the secondary coil. We know that the ratio of the input to the output voltage in a transformer is the same as the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. So that's input voltage, 240 volts, divided by output voltage, 20 volts, equals primary turns, 300, divided by secondary turns, Ns. If we rearrange the equation, we get that the number of secondary turns equals 20 divided by 240 multiplied by 300. That's 1 over 12 times 300, that's 25 turns. On a large scale, power stations use many electromagnetic effects. Steam or falling water turns the turbines, which turn a generator, which generates an alternating current. Transformers step up the voltage so the electricity can travel along distribution cables at a high voltage, and other transformers step the voltage down to a safe level for consumers to use. That's the end of the higher tier section on energy resources and transfers.